Okay, friends, let's start the next lecture. So today, in this lecture, we'll be talking about heavier quarks because the last lecture, last 2-3 lectures, we have been talking about the light quarks and theories describing how, meaning their effects essentially, like theories like chiral perturbation theory and lattice gauge theories, which are useful to compute things in uh, for lighter quarks, which are essentially the U, D, and S quarks. Today we'll try to discuss more about heavier quarks. So you know that the nature has 6 quarks. So we discussed about the light quarks, which are U, D, and S. Before going to moving to the heavier quarks, let's just say one word. The kind of theories we discussed, okay, quantum field theories. Theories we have discussed so far. Meaning the ones which we have discussed, essentially like chiral PT, perturbation theory, or lattice gauge theory. So these are theories which are valid only up to certain scales of energy or length scales. At least the kind of theories which were these are all so essentially these are not full quantum field theories which are valid for all energy scales or all length scales. Okay, so that okay, if you have very short distance, that means very high energies, it won't work. So if, for example, in this case, these theories are for q square around lambda qcd or length scales around a Fermi, a bit smaller than a Fermi or so. Okay, but you don't really go into say hundreds, one say 10 power 2, 10 power 3 times the Fermi. So this is not really very high. Say for example, you are not going to energy scales which are like q square is equal to hundreds of 10 GeV square or more than that. These energy scales are not covered in this particular case essentially. So these are field theories which are only valid up to certain scales. So such kind of field theories are called effective field theories. So these are field theories which are only valid. These are quantum field theories which are valid only up to certain scales. This scale could be energy, okay, or in length, or whatever. I mean, there could be anything. So okay. So the theory. So we so far discussed about the light quarks theories. The theories which describe light quarks will not be applicable for, say, theories with heavy quarks, or theories with other quarks. We know that there are other quarks in nature which have been discovered, like for example the charm quark. The charm quark also forms mesons. And perhaps baryons also. But mesons have been discovered. These mesons are called D mesons. Okay, these are classified into two. So one is DS mesons, which are essentially with strange quarks, D mesons without the strange quark. So when the charm quark sits with the strange quark, then these bunch of mesons which you can form are called D mesons. And and when the charm quark sits with other mesons, say U and D, these are called D mesons without any suffix. So the D mesons these are being studied essentially, say most of the time. The charm quark C is like the up quark and its quantum number. So that means C, if you take the C, it has a charge of -2/3. It's a fermion spin half. Of course, all the quarks are fermions. Its flavor is called charmness, and later on we will see the hypercharge is the same as the hypercharge of the up quark, which is essentially 1/6. But anyway, we'll discuss this later actually. So the same meson has almost the same, except for the charmness, almost the same quantum numbers as the up quark. So so if you want to form, say for example, a C D plus meson, so this would be, so C D bar. Okay, this would be a CD bar, and this would be a D meson. Then there could be a D0 meson, which would be C U bar. Okay, in which there is a C, the mass of the C is much heavier than the mass of, say for example, up and down quarks actually. So the mass of this is, if you remember, in I think in one hour I am just trying to search which is the lecture where we introduce the C quark. The C quark is in the we discussed C quark when we discussed you remember gypsy meson essentially. So the discovery of the gypsy was essentially led to the discovery of the charm quark. Okay, so the D meson is much heavier. It is more than a GeV actually. So it is about say around gypsy is around 2.5 3 GeV. So the mass of the C quark is around 1.2 GeV. So around 1.2 GeV. So this is quite a heavy, reasonably heavy quark. So you can have the gypsy, which we have, remember that it's around a CC bar bound state. Okay, it's around 2.2 gypsy bound state actually. So now if you look, and there are various other possibilities actually. Now D mesons, so you can construct all of them, and similarly ds mesons also you can do with cs bar would be ds plus, and ds0 would be c. Sorry, that's not ds1. Okay, and d minus is essentially c bar s. So you have all these mesons with one heavy quark, and the others typically light. Okay, typically light, but this difference between okay, so the d mesons is not really this the d mesons are one of the hardest objects currently. Hardest objects to understand theoretically or from first principles, like putting on lattice or any of these things. Okay, uh, to understand theoretically what is the meaning, all their form factors, etc precisely. So experiments are also working on it. Okay, but theoretically they're one of the hardest objects actually. So why do you say meaning these objects do not have enough tools. There are not enough tools, meaning field theory tools. There are uh, not enough not enough good field theory. There are actually field theory tools to understand them, as well as other mesons. So okay, so the say for example for the light quarks, say UDS mesons and everything, you have the chiral perturbation theory, you have the lattice and everything. The D mesons are somewhat in between. Then there is a B quark. I'll tell you why I mean say that, because if you go to other heavier quarks, like for example the B meson, so B mesons are essentially made up of one B quark and other quarks. So, so you have BD 0, say B bar, one combination BS0, which is BS bar. Okay, these are two BD bar, and then you have B plus, which is BU bar. Okay, similarly you have other strip. So you can construct so B minus would be um, this is B minus, sorry, B plus would be BU bar, B bar U, and so on. Okay, so there are so again anything with meaning with one quark essentially, uh, and then the rest of the other quarks you can form all possible bound states. Of course, you will also have the BB bar bound state, which is called the upsilon. there is a BB bar bond state, which is the epsilon 4s, which has been discovered later on. Okay, much later than the gypsy. Okay, which is a CC bar bond state, and the B quark is has quantum numbers like the down type quarks. So the down type quarks. So the B, the quantum numbers are small b. Sorry, not the big B. So big B is the meson. Small b is the quark, which has charge -1/3, and it has bottomness, which is the flavor quantum number, spin half, of course, same thing, and hypercharge 1/6, and B right has a different hypercharge. We'll come to that essentially. Okay, we'll come to that hypercharge later. And isospin would this is -half. Now the B quark mass is pretty large, is around 5 GeV. So all the masses we have seen so far are around, let's say, tens of MeV. Okay, so for example, up and down type quarks are essentially around tens of MeV. S quark, a strange quark, is around 90 MeV or 200 MeV. So then there is the charm quark, which is around again 100, 120, 120 MeV. 1.2 GeV, sorry. That is strange quark is around hundreds of MeV. The first GeV one we saw is the charm quark, which is around 100. Okay, about thousands of MeV, which is around a GeV. Whereas so the bottom quark is even heavier than the charm quark by roughly about a factor 4, 4.5 or something. MV is around 4 times MC. Okay, and of course it's much larger than MS, much larger than MU and MT. So what one can there are theoretical techniques one can use to understand these things. So all the mesons which are formed, okay, with in the bottom quark, like the ones which we have seen, all the BS, BD mesons which have been studied both experimentally and theoretically so far, uh, they have been studied well, and they're okay. So they use techniques. Theoretical techniques are the typical theoretical technique is it's called heavy quark effective theory. HQET. Now the so this same heavy quark effective theory is also used also to understand charm quark. charm mesons. Okay, not just B mesons, but it works far more better for, say, for example, for bottom quarks or bottom mesons compared to charm. Okay, it works far more better. So the basic idea is that so the basic idea is that if you have a heavy hadron, so it rests on the fact that if you have a meson, so for example, so there is a bottom, or say for example a bottom meson and some constituent quark, some say for example D. Okay, okay. Now the bottom mass, so these will have energies, the constituent quark is the are essentially the light quark are the light quark, which is essentially this one, and the heavy quark. The idea is that this quark is very heavy, so its mass is, so it's almost like non-relativistic. It doesn't really move, and whereas the MD, okay, MD, say for example, would have momentum, so up to say similar orders of lambda Qcd. Say for example, that's around 300 MeV. So which is very small, essentially 200 to 300 MeV. So the total heavy quark is almost meaning on the on shell essentially. So the heavy quark is almost non-relativistic. Okay, it's almost always on shell. That means it doesn't have a propagator. Essentially, it's not a really virtual particle. It's really on shell, and also its mass mq, the heavy quark mass, would not have much momentum essentially. So mass would not change. So this would be of the order of lambda Qcd. The total meson would be dominated by the heavy quark, dominated by quark, mass of the total meson plus some order, say plus some order lambda Qcd. So this is so this reminds us that uh, of the hydrogen atom. So Again, to sum up, the basic idea is that the heavy meson or the heavy hadron, essentially in this case, particularly if it is a containing a heavy quark like a B meson and also the charm meson, say for example, both of them are used. But like I said, most of the time the heavy, the for the bottom mass it works very well. But let's just go ahead and say for the both for the charms and farm and the bottom masses. So what it says that now, because there is a very heavy meson, it's almost like it cannot really move. Okay, and so whatever constant, meaning virtual moment which they can take, or the off shellness they can go beyond their mass shell, would be of the order of lambda Qcd. But the heavy quark inside the hadron, inside the heavy hadron, is already very heavy. It's several orders of magnitude, or it's several factors larger than lambda Qcd. Say, for example, the B quark is almost 10 to 15 times lambda Qcd. So it is so whatever momentum you add of the order of lambda Qcd, okay, to it would actually make any difference actually. So it will just remain there. It won't really move much. Essentially, it's almost like a stable thing. Whereas the constant light quarks can move up to a lambda Qcd. So typically quarks inside, you would expect inside a baryon or something, would have momentums of the order of lambda Qcd, right? And that's sort of the basic idea. So, but for the heavy quark, it won't move much. So, any addition to its momentum would be very small, as long as it's inside the baryon or the meson essentially. So, in such a case, so you can actually use simple things like, for example, the you can actually use the momentum pq of the heavy quark to be equal to pq times v. It's almost like a non-relativistic case plus k. Okay, so this is the heavy hadron momentum or heavy meson momentum. Okay, and k is of the order of lambda Qcd, variations of the order of lambda Qcd. Okay, so you can use this approximation and then use this in the propagator itself. So, for example, if the B quark is moving, the B meson is moving, you can just say that the B meson velocity, the velocity of the B meson is nothing but the velocity of the heavy quark, of the B quark inside the B meson, plus some corrections of the order of, say, for example, k, which are of the order of lambda Qcd. Okay, so with this you can actually use the Taylor expansion, and so v is the velocity. So you can make a series expansion in 1 by mq. Okay, so in terms of the heavy quark, you can make a series of expansions, and this is like saying that the heavy hadron or the heavy what do you call, the heavy meson essentially is dominated mostly by the what do you call, the heavy quark inside the hadron. So you can actually use that information and do an expansion in terms of the heavy quark mass actually. So this is again an effective theory. and this is called actually this is called heavy quark effective theory. Now, this is used to understand, say, B mesons, typically used to understand B mesons and some and also charm mesons. Okay, but it works very well with the B mesons. Like I said, I don't. Okay, I don't want to repeat it. In certain cases, it also works very well even with charm mesons also. Okay, and then finally, the last quark we have. The last quark is a top quark. The question is, does top quark form mesons? No, actually, because the lifetime of the top quark actually is very, very, very small. Is very, very small compared to the lifetime of the hadronization. So imagine that these are quarks which are formed as quarks. Like for example, we will see in diagrams in perturbative Qcd. So they are formed in collisions of this proton, say for example. So proton is coming and then it hits and gives you some quark like top quark, say for example in a collider, and then you produce a top anti-quark pair. Now this top quark has a mass mt. One of the most important parameters in standard model is 175 GeV. So mt is 175 times the mass of the proton. Imagine that this is a quark which is roughly 200 times heavier than proton, which is a bound state of the 3 light quarks actually. Now, whereas this is not a bound state, this is just top quark. The top quark hadronization time, meaning, so the once it is formed or the top quark is formed in this thing, it should form bound states. The typical hadronization time, the idea of this is the top quark. Then this top quark is a fermion. Then it emits out various particles like gluons. Okay, and these gluons and then produce top anti-top quark. We'll see that in continuation of this lecture. So this will form bound state. One of these tops will come with another top, anti-top, and so they will start all forming some bound states essentially. The formation of these bound states is called hadronization. And the time scale tau hadronization is around 1 lambda Qcd. 1 by lambda Qcd. Whereas the lifetime is much smaller than 1 by lambda Qcd. The lifetime of top quark, essentially tau top, is much less than the lambda Qcd. So the top quark decays before it can hadronize. So which is very amazing because here you have a top quark which is almost like, you think that it is like a free particle, but its lifetime is so small. Okay, its lifetime is so small because the heavier the particle, typically the lifetime goes uh, it goes proportional to the mass of the particle. Actually, so in some powers of mass of the particle. Okay, if it is a t-body. Okay, so and so as as the particle becomes heavier and heavier, it's more likely to decay very very fast. It's more like, unless there are some symmetries, and of course there are interactions, and what kind of interactions it take place, a number of things, of course. Okay, so assuming, so if these are typically, if it decays by weak interactions, so just imagine that it just decays by weak interactions. In such a case, the heavier the particle, the faster it decays. Okay, the heavier the particle, the faster it decays. So, and in the case of top quark, it's so heavy, okay, that its lifetime is actually smaller than 1 by lambda Qcd. So that means it doesn't even have time to hadronize. So, and it just decays. It decays very fast, and it doesn't have time to hadronize. And so you only you by the time, okay, it doesn't, okay, so you don't have any bound states. Okay, you don't have any bound states with any top quark. So the end result is no. So we don't have top mesons. So no top baryons. Okay, mesons or baryons. So top is such a interesting particle actually. Okay. Uh, okay. So now, so we have seen all this. We have glimpsed about all these mesons. Okay. And these mesons, say for example, with the charm, we can also ask the question whether we can. So, are the only things which are possible? Like, for example, you not have, say, something like four Quark bound states. Yes, they are possible by, and we believe that we have seen such bond state. Because QCD allows them. QCD allows them because you can always again have a four quark bond state, which is actually a singlet. Okay, which is a singlet in color. So that is quite a possibility. Okay, so this kind of states are called tetraquarks. Again, the question arises whether one should treat, how do you treat theoretically tetraquarks? Does its spectrum actually look like a molecule or like a diatom or whatnot? Meaning there could be all these things are still being understood. Meaning depending upon the system of meaning we don't have enough. We didn't study enough tetraquarks to understand this system. Okay. Similarly, there are ideas that there could be also pentaquarks. Okay. So quark are also possible. These are called pentaquarks. So the experimentally people are looking for them. And theoretically, yes, they are possible. QCD allows these bond states. But whether they're stable, whether they can be studied experimentally or not, this is the good meaning. This is the question which is not experiments should solve. Actually, we still don't know actually completely. So with this, I think I covered most of the points which I have wanted to cover about the meaning bound states of QCD. Okay, so we covered the bound states of QCD, and also, as I said, this bound states of QCD is only valid. Okay, when the energies of the system or the, say for example, or the bound particles, like for example the light quarks, are around q square is around lambda qcd. Okay, around lambda qcd square, and the what do you call, the length scales are around a Fermi or so actually. Now, what happens if you start going for higher energies? So, when the quarks start having higher and higher energies, so and what happens when quarks start going into higher energies, and then you start probing smaller and smaller length scales. So, this we enter the regime of perturbative QCD. So now let's start discussing from now on ideas related to perturbative QCD. So let's continue on perturbative QCD. So perturbative QCD goes deep inside the hadron or the meson. So at energy scales, for that you really need very large energy scales. So energy scales of the order of which are much heavier than lambda QCD. So typically it should be much greater than a couple of GeV squares, say for example 2 GeV square. So in those energies, the substructure of the proton or the meson or the baryon is seen and these are the regimes where the quark acts really like a free particle, which we said essentially act as though they are free particles. So the theory which describes the situations or at this energy scale, the quantum field theory, which describes the nature of physics at this case is also called quantum chromodynamics. In this case is called quantum chromodynamics, or simply QCD. Now, what is the theory of QCD? The theory of QCD has the following features. Every quark, essentially, which is a Dirac fermion, comes in 3 colors. So that means every flavor of quark comes in 3 colors. second thing is that the Lagrangian is locally invariant under a color SU3 symmetry. So what does it mean? That there is an SU3 gauge theory which is locally invariant, and this locally invariant SU3 gauge theory is actually a color symmetry. It's a color theory. Okay. The symmetry is unbroken. The color is always conserved. So it's like electric charge in the case of QCD also. The color, it's like the replication of electric charge, which is always conserved. In QCD, the color is always conserved. Okay. So let's try to write this theory. Okay. So then we'll see experimental phenomenology and stuff like that later, maybe in the next lecture or so. So we know how to write gauge theories. So let's write QCD gauge theory. Okay. The Qcd gauge theory would be some psi prime is equal to e power I theta. Now it's a local gauge theory. So this theta would be how many? First of all, let's see. It should be a member of. It should be local. So that means it's a function of x, and then how many thetas would be there? How many generators of QCD? So there will be 8 generators times psi. So there are 8 lambdas. A is equal to 1 to 8. Okay. So this should be your SU3 local gauge transformation. So normally how do you write for the colors? So the color would be Si would be, this could be any quark. Okay, we'll come. So psi q, where q is equal to UDSCTB. All these 6 quarks individually they come in so essential 3 colors. So they will be say psi QR, psi QG, psi QRGB. So this is a triplet of SU3 color. Here the C is subscript. Okay, subscript stands for color. So this is to distinguish from the SU3 of the flavor which we have seen in the previous lectures. Okay. Now with this I want to write down my Lagrangian. So let me just write down initially how will it look like. The Lagrangian, okay, the Lagrangian would be I psi bar I del slash psi minus m psi bar psi. That's it. This is your Lagrangian. Okay, sum over all Q. Now this is slightly complicated because there are weak interactions which are responsible for the masses. So for the present we'll just say that okay, there is some, so as we write it down for one quark. Okay, where Q, again we defined Q, actually where it is. Now what is D slash? D is equal to del mu plus I gs lambda A g mu A. Now how did I write this thing? Okay, so how did I, so what did I do here? I know the generators of, what did I use? So here first I used that lambda, there are 8 generators, lambda A are 8 in number, okay, because SC3 is a symmetry of, we have SC3 is a 3 by 3 matrices and it has 8 generators. So special unitary 3 by 3 matrices, it has 8 generators, and these are the Gell-Mann matrices as we have seen earlier. Okay, we have seen this already. The second information I would use, I used is that for local gauge theories, okay, there is one more term here which is called L alignments. We'll write it down. For local gauge theories, what do I have to write for an invariant Lagrangian? Del mu has to be modified in terms of del mu is equal to del mu plus IGS. Now for abelian gauge theories, there was the, for U1 QED, so the generator is only unity, but in the case of non-abelian gauge theories, the generators are large in number. So how do you write it down? So you write it down in terms of generator times W mu, some G mu A. So generators times some fields which are essentially your photon fields corresponding to the 8 generators. So the number of generators should be equivalent to the number of photon fields. So this would be the so-called photon fields corresponding to each generator. And so these are called gluons. So these are called gluons. Okay, they are 8 in number corresponding to each generator. So A is equal to 1 to 8. Now there is another point we have to remember in non-abelian gauge theories. The gluons can interact with each other. So what do you mean? How do I get this information? So how do I see? I have to write down. You remember that for photons, say for example, let me just remind ourselves for the photon. For the photons, we wrote down something like L photon A is equal to minus 1 by 4 F mu nu where f mu nu is equal to del mu a nu minus del nu a mu. The kinetic part of the photon fields this is essentially the kinetic part of the photon fields. Now if you ask the same question, say for example for the gluons, okay, because the theory is non-abelian, things are completely different. Say for example for the gluon fields, for the gluons you should also write the same thing, but it is called ym because it is something called Yang-Mills. So this is given by g mu nu, but for each photon there is a g mu nu, so there is another g mu nu and a g mu nu. So there is a kinetic term for each gluon. Further, it just doesn't stop there. Okay, g mu nu a is equal to del mu g nu minus del nu g nu minus f a b c g mu b g nu c. So the kinetic terms of the gluons are 8 in number, and furthermore they are coupled bunch of equations. They are coupled bunch of equations. Kinetic terms of gluons are 8 in number, and furthermore they are actually coupled. They are coupled with each other. That means gluon 1 interacts with gluon 2, gluon 2 interacts with gluon 3, and so on. So what you have, this means that the gluons okay, interact with each other. So this coupling is essentially showing that it is an interacting theory. The gluons on themselves can have interactions. Okay, so you don't need quarks. You don't need quarks to have interactions. So you can have interactions purely with gluons essentially. Now this FABC is given by the SU3 indices essentially. So it is given by structure constants of SU3 essentially. So this means you have a theory, the gluons interact with each other, so they have strong interactions among themselves essentially. So they have strong interactions amongst themselves. And why is this so? Because the gluons also carry color. So the point is that the gluons carry color and they can interact with each other, and this is completely new compared to what you have in the case of say electromagnetic theory. So this is a theory in which it's much more powerful than electromagnetic theory. It's much more complicated than electromagnetic theory, in which the photons or the mediators of the force themselves interact with each other, and that's because they carry the colors. Now if you take, if one takes as 3 is equal to RGB, these are the three colors, the quark of the, okay, so what we wrote down earlier, and 3 bar is equal to R bar, G bar, B bar. You know that 3 times 3 bar is equal to a singlet plus an octet. So the gluons sit in the octet. Okay. These octets essentially take the structure coming um, from the generators are given as, so that means they carry color. So that's what I was saying. So uh, these octets are given. So similar to from the generators of the C3, the lambda, the Gell-Mann generators, you can actually write them down. So you have the first state would be, say for example, the first state would be RB bar plus BR bar. The second state would be I of the same thing, as so minus I, RB bar minus BR bar. The third state would be RR bar minus BB bar. So you can see this is the diagonal generator, right? Okay, so you can see that this is the diagonal generator. Fourth state would be bar, and similarly you have the next state. One second. Fifth state would be minus I, RG bar minus GR bar by root 2, and the sixth state would be BG bar plus GB bar by 1 by root 2, and the seventh state would be minus I, again with the minus sign, BG bar minus GB bar by root 2, and the eighth one also would be a diagonal generator, so it will be RR bar plus BB bar minus 2 GG bar by root 6. So these six, these six would be the these 8 would be the generators of the or the gluon fields, and note that all of them have color in them. All of them carry carry color, except even the diagonal ones, say for example, except for the diagonal ones, like something like the 3 and 8. So there essentially you have the diagonal ones would have so RR bar, BB bar sort of thing essentially. The diagonal ones are sort of have these are essentially have BB bar, RR bar, and GG bar, and also this one RR bar, BB bar. So and then there is also one ninth state which is essentially the singlet state, and I don't know what to call it now. The singlet state made up of the gluons made up of purely gluons would be RR bar plus BB bar plus GG bar by 1 by root 3. So this would be a singlet. Okay, so this would be the singlet state. These are the possible combinations you can have with the 3 colors. We have seen this thing, no? This is would corresponding to the sort of the eta prime of the gluons essentially. So instead of 3 quarks, instead of the flavored symmetry, you are making a singlet state there also. Okay, here you are making with the gluons, because the 3 gluons will like the 3 colors of the gluon would correspond to the 3 colors of the quark would correspond to 3 flavors. So you can think of constructing octet state as well as a singlet state, and that's what we have done actually. So let me ask the question: Has this thing okay? I'll ask it later on actually. Okay. So with this, now you see that the gluons carry color. Okay. So there are these 8 gluons, and then these carry colors. So the total Lagrangian of the QCD is given by L QCD is equal to psi bar I del slash psi minus m then psi for each quark, okay, minus, okay, Langmuir is essentially G mu nu A, G mu nu A. Which is the essentially F mu nu term corresponding to gluons. So with this we can I write down the Lagrangian of QCD. Okay, we have the Feynman rules of the QCD. Okay, so which are given by so what we need to introduce before, so the Feynman rules introduce, so before that, so what it introduces is QCD introduces a new quantum number which is essentially color for each quark and gluon. Okay, this is important actually. Okay, So it introduces for each quark. So what you need to do, so for RGB, so for if you have red color quarks, say for example, so we'll introduce one column vector which is 100. Okay. Similarly, for a green color quark, we'll introduce another column vector of this type. So somewhat like a spin, somewhat like a spin. So for okay, for a blue color, we introduce something like this. So let me call this column vector in general. This column vector, a column vector represents the color. Represents color of the quark. So let me call this as C. Okay, we call this as some column vector C. Similarly, for the gluon also you'll have something else. So we'll call it as A. Okay. So with this, so what we need is to write down explicitly what these quarks are essentially. So for an incoming quark, so we'll come to gluons in a second actually. So you write the Dirac spinor U with a particular spin and a momentum, okay, UPS. Then you also introduce a color factor here, a color, okay, color vector here. So the incoming quark, so this is a vertex and then quark. Now outgoing quark will be U bar P as C dagger, outgoing quark. Now for an incoming anti-quark, it's very similar to the case of QED. So this is an incoming anti-quark, it will be V bar with a particular spin and S and C bar. Then you have an outgoing anti-quark which will be just V. Now for a gluon, gluons are all like any gluons are massless. Massless as the symmetry is conserved. I think we spent enough time on this essentially. Okay, so for an incoming gluon, what do you write is the polarization vector. So you just have two polarizations. Again, remember that gluons will have, okay, two polarization vector with the P. Then you also have a color vector which is A alpha. So then an outgoing gluon, so the gluon would have an alpha here. So the gluon would have two colors, remember that, okay. it's a combination of color, anti-color, or whatever, meaning it will have something like that actually. Okay, so whatever it, we put it in alpha, whatever it be it. So then outgoing gluon, incoming gluon. So this would be epsilon mu star of p a of alpha star outgoing gluon. Okay. So these again are your color factors. These are color factors. So which exist independent of this thing. So the propagators for the quark anyway would be propagators would be I q slash minus mf. Same, okay, similar to that, and the color factor is sitting with making sure the color passes through essentially. Okay. Then the gluon propagator would have again the same sign. Then the Lorentz index mu. Then there is also the color index alpha and beta. So this would be very similar to eta mu delta alpha beta q square. So this essentially ensures the incoming color and the outgoing color is the same. So just like eta, so this gives okay, just like the charge is always conserved. So here is the delta alpha beta is ensuring that the gluon color is not changed during the propagation. Vertices so first we have quark gluon vertices. So this is has quark a gluon. Now the point is the gluon also carries color. Okay, the gluon also carries color. So you could have, say for example, some very interesting color factors like this. So the incoming color would be, say, anti-red, and the outgoing color could be blue, so on, so possible. Okay, so but in general, this is quite a possibility. Okay, so all this are possible depending upon the factor which is sitting here. So this is given by, so normally this lambda I is not there. So depending upon I and j of the quark, okay, you would have essentially what is this factor sitting in. You can put that also essentially. Okay, then they have vertices which are more complicated, which is essentially the three gluon vertices, which is given by minus I gs f alpha beta gamma times some Lorentz invariance factors depending upon the moment, actually, because it's a moment independent vertex k1, k2, k3. So this is g mu nu, which is a antisymmetrization of lambda plus g mu lambda k2 minus k3 times mu plus g lambda mu k3 minus k1 times mu. So then there is the 4 gluon vertex also. This is the 4 gluon vertex which has the following form. This is again somewhat like we saw in scalar QD, independent of the momentum. So we can put we don't forget about that, but it's dependent upon the color factors and the Lorentz indices. So if you put the color, I'm just writing the color factors alpha, beta, uh, alpha, beta, lambda, rho, say for example, then you'll have something like f alpha, beta, eta, alpha, eta times symmetrization mu lambda times mu rho minus mu rho mu lambda alpha delta eta f beta gamma eta g mu nu g lambda rho minus g mu lambda g nu rho, and finally you'll also have one more term which is f alpha gamma eta f delta beta eta in terms of g mu rho g nu lambda minus g mu nu g lambda rho. Okay, so this is all the 4 vertices, okay, where a repeated vertices is essentially summed over. So just to repeat, these are the this is the vertex, and these are the essentially incoming gluon and outgoing gluon given by the polarization vectors and the color vector factors which are sitting in front. The propagators are given in terms of this I q slash minus lf for the quarks, and for the gluons they have the color factors associated with the gluons are alpha and beta. So there is an eta mu nu times delta alpha beta, just to make sure that the color is conserved at during the propagation of the gluon, and the rest of the propagator is exactly like that of a photon. And if you look at the vertices, the quark gluon vertices is given by IGS by 2 lambda A times gamma mu. The lambda A is the new one which is essentially associated with the generators of the Lorentz SU3 color group. Lambda is, and the Ij indices would be the Ij indices of the incoming quarks. Or the elements of this thing would be corresponding to the elements of the quarks, incoming and outgoing quarks essentially. So one interesting thing would be, say for example, I drew red and blue here. Essentially, the red could be the outgoing color, and the blue could be this kind. Sorry, the arrows are not correct. Uh, so a red could be the incoming color, and whereas the blue could be the outgoing color, and the gluon would modify the color of the quark. Say for example, a red color quark into a blue color quark, depending upon what is the generator it sees. Essentially, if it sees uh, 1 2 or 1 3 or a changing generator, then it's, if it's a diagonal generator, it wouldn't do that actually. Okay, and similarly then the most interesting things are essentially the three gluon vertices, which are given by this. This is a momentum dependent vertex because dimensionally this has a momentum dependence. Now if you take the three momentums as k1 k2 k3, and it is also appears at first order perturbation theory. It is just proportional to Gs. This has a form of this particular type essentially. So G mu nu times K1 minus K2 lambda, G mu nu minus K2 minus K3 mu, G lambda mu times K3 minus K1 mu. Finally, you have the four gluon vertices, okay, which goes as Gs square, so this is second order in perturbation theory, which gives you which is momentum independent, but it has a combination of several SU3 structure constants, which are essentially F alpha, beta, eta, and various these things. Here I have chosen alpha, beta, lambda, rho as the color indices, and over the color indices you end up having this kind of a combination essentially. I didn't put in the Lorentz indices, but okay. Okay, I'll leave it as it is right now. Essentially, one can look it up in some textbooks or something. Okay. Textbooks like the ones which are shown in the structure essentially. So with these things, in the next lecture we will play with some simple process in QCD. Say like we'll try to replicate the simple process try to simple process what we have seen in QD, and so something like quark anti-quark going into glue player, glue going into quark anti-quark, Q glue going to Q glue, okay, and so which is an replication of Compton effect, pair production, then also pair annihilation, and Bhabha scattering. Okay, and then we'll also do Compton effect sort of thing, which is Q gluon times Q gluon. Okay, so these are the effects. We'll try to see some effects and try to write down simple amplitudes like what we had done for QD, and then we will see what is the difference between QD and QCD, because here always there is a factor associated with the color. The color factors play an important role. They enhance the production cross section by a factor associated with the colors of the by a factor which is essentially associated with the color factor. Okay, so we'll stop here, and maybe the next lecture we'll look into it in more greater, and then we'll also do asymptotic potential things. Maybe in 1 or 2 lectures we'll try to finish QCD actually. Okay, I'll stop here.